Let's take a look at using a graph to write an equation for a rational function. And we've been dealing with rational functions from here on out, so you kind of recognize what's happening with behavior around asymptotes and such. So what I like to do is start off with what I know for sure just by looking at the graph. If there's nothing else indicated, I won't be able to tell any other information. So let's take a look. At first, we see we have our vertical asymptotes right here. There's one, VA, and that one is at x equals 4. And then there's another vertical asymptote. That would be at, as far as estimation is concerned, we're going to look at x equals -3. Now, a little bit of study with the rational functions is that vertical asymptote factors show up in the denominator. They're what makes the denominator undefined, or I should say what makes the denominator 0, which makes the function undefined. So starting off, just kind of piecing things together, we're going to call the function, our favorite, f of x. And as far as we're concerned, it's rational, so we're going to start with the fraction bar. The vertical asymptotes will tell us what our factors of the denominator are. So just so that we're looking at this, if x equals -3 is what makes the denominator 0, then the factor should be x plus 3. So we'll start off here. And I'm going to deal with the multiplicity in a second, but I just want to get the general sense of what the denominator should be. So if we have the vertical asymptote, what makes the denominator 0, x equals 4, we know that the factor should be x minus 4. So we have the two factors in the denominator that are clear for us. Now, there's also important information to be had by looking at the graph. We can tell what the multiplicity of each factor is based on the behavior of the function dealing with its asymptote. So like what's happening as we're getting closer to the actual vertical asymptote from the left and to the right. So what I like to inspect right now is consider what's happening at x equals -3. So that we're having over here. I'll color it in for you. And what we're particularly interested in is what is our function doing as x approaches the vertical asymptote from either side. So if you notice, I'll use some arrow notation for a nice review for you. As x approaches -3 from the left-hand side, then our function, notice how it shoots down really, really fast. Our function is approaching -infinity. Now, similarly, if we look from the other side, as x approaches -3 from the positive side, what is our function doing? And we can kind of see on this side of the asymptote, our function is shooting up to +infinity. So whenever you get the behavior of the function shooting up at +infinity and down at -infinity around that vertical asymptote, we have our case of what we consider the factor will have an odd degree. And remember, that's the reason why is that we have different infinities. One's shooting really high, one's shooting really low. So right away, the factor x plus 3 should have an odd degree. And we're going to keep this as simple as possible. I'm not going to start off with a big odd number. I'll just remember that odd means 1, 3, 5, 7. I'll just start off with a 1. And let me write that in green so that we can color code that. If we need to bump it up higher, we'll move to 3. But usually in these types of problems, they don't give us enough information to determine that. So we'll start off as small as possible. Now, same story. I want to look at the behavior around the next asymptote. So I'll use purple to help you. And just consider this. Again, we're looking at 4. So let me see if I can clean things up a little bit for you. So again, my focus again is what's happening at 4. And so as x approaches 4 from the negative side, so what's happening here, look at what our function's doing. It's shooting down very, very fast to negative infinity. And as x approaches 4 from the positive side, our function itself looks like it's shooting down to negative infinity as well. And so what happens is when you both have the function shooting down to the same place, both negative infinity or both positive infinity, what you end up having for that factor is an even degree. Let me do that in purple so that we're color coding it correctly. So as I said earlier, we always start off with very small numbers and we can raise them if we want. So even numbers, 2, 4, 6, 8. We're going to start off with having that degree at 2. So I'm filling that in. So we'll start off with that. The next thing we're going to consider is, remember, we got to figure out what should we have in the numerator. Well, if I'm dealing with the numerator, I'm probably going to address what's happening if I have any x-intercepts. So I'll clean this up just a little bit. And I do see right away we've got ourselves an x-intercept. So let's see, I'll do that. I'm using up all of my colors. I'll do that with pink. And notice we have our x-intercept at x equals positive 2. So that's going to tell us that the factor is x minus 2. So right away, we can include that in the numerator. Now, the last thing we want to do with that factor is determine what its multiplicity is. And based on its behavior, whether it's crossing the x-axis or whether it's bouncing off, sometimes we say tangent, we'll help ourselves out with figuring that out. And so you can see right away that the function appears to be crossing the x-axis at that particular value, x-intercept our root. So we know right away we should have ourselves an odd degree. So I'll put that in there for you as well. So again, since it crosses the x-axis, we'll have ourselves an odd degree. And again, with odd numbers, to start off small, we'll start off with a 1. And you don't have to really write the 1 in there. It's just there to help us keep track of what we're using. So we are almost there. You'll notice if you try to enter this in on your TI, it's not going to quite look like it has to, the actual function. See if I can demonstrate that with you. Sometimes it takes a little while to warm up that TI. So let's see if we can do that. I know sometimes we don't have the best. I have a previous function. So let me go back and zoom the window in to standard. So that's zoom, and I'll select item 9. And nope, didn't quite do that. Let's try that again. Oh, that's why. Zoom standard is 6, excuse me. There we go. Okay, so let's try to enter in what we think the function was. And so again, I'm going to scroll back really quick just to view what I can write in. So x minus 2 in the numerator, x plus 3, x minus 4. So I'll try to remember that. I know it's nice for you because you can view your paper right away. So remember with rational functions, we're going to enter this in. We have x minus 2 in the numerator, and then we have divided by. And I use a double parenthesis because I need to indicate that there's two factors in the denominator. So I should have an x plus 3, close parenthesis, and an x minus 4. Close that other parenthesis, and again, close the denominator completely. So notice when you graph it, it looks pretty similar to the picture. Like in terms of what's kind of happening, you can say, well, there looks like the middle part looks okay, but kind of compare back. And notice, check this out. Notice that there was some interesting movement on the top part of your axis. So it's not quite looking the same. I do kind of see the middle part coming into play. But there's one more thing that's going to give us more information about our graph. And we call this the stretch factor. Actually, I should, let me go back. I think I forgot something. I was very excited to show you the stretch factor, but let me go back. I believe I forgot an exponent of 2 in that denominator. Sometimes that helps, like just taking a step back and looking what you are doing. I apologize. Sometimes when this is right in front of us, we can't see what's happening. So let me insert that. I think x minus 4 was supposed to have that exponent of 2. And that might also explain why our picture is looking different. All right, let's see. I'm going to insert exponent of 2. Let's see if that changes anything. It's kind of nice that we go over this because, you know, we're not always perfect. We can kind of see what's happening. Oh, and that made it even kind of way different. So it's still kind of bothering me. I see that the asymptotes are still there in the right places. I don't know if you can see my cursor. But again, I believe the original picture, there's the two end branches. The left branch looks like it was around below the x-axis, and the right branch as well looks like it's below the x-axis from our original picture. And it looks like our function is kind of backwards in the middle. So it looks like it's decreasing from left to right as opposed to increasing. So again, I mean, it didn't really leave me with much, but I kind of have the idea. But what we're more interested in, this is what I was so excited to talk about, is really considering we need something a little bit more precise. And notice with our particular function, we saw that there is a nice y-intercept. And if you go back to your TI and you're inspecting this with the graph, notice that it looks like the y-intercept's at 0, and that's not correct. So let me go back one more time. One last thing to decide for ourselves. And I'm going to erase out a few things so that we can keep this all in one screen. We're going to look at how we determine what the stretch factor is. And back in when we were describing transformations of functions, we notice if a function is vertically stretched, there's usually a constant in front of all of the functions. And so this is where my stretch factor is. It's getting multiplied to the entire function. And how we determine what that stretch factor is, we don't really have to guess if we know some clear points on the function. So right away, I can tell some very clear points on the function. There's the y-intercept. And there's also the x-intercept, which we use to help us determine our factor in the numerator. Those are for sure points. Everything else is kind of like a guess. So if we're going to use an ordered pair to help us figure out what this stretch factor is, we're going to use something that makes it easier for us to kind of solve this particular function. So remember the x-intercept, its ordered pair was 2, 0. And then the y-intercept, its ordered pair is 0, 1. And either one would be fine, I just know from experience that if I chose the x-intercept and I'm trying to plug this into my function, I would have to make the f of x equal 0 and then solve for the x. And that is fine. You can plug this in, x is 2, and go from there. But sometimes that causes a little bit of trouble. It's a little rougher with calculations. Not that you can't do that, but I always like to go the nicer way first. So I'm going to use the y-intercept to help me. And what that means, as far as the stretch factor is concerned, I'm going to take the f of x, which is a times x minus 2, x plus 3, x minus 4, and I will plug in my ordered pair. So remember, my ordered pair, 0, 1. So that's indicating that when x is 0, the f of x is 1, or we call it y. So right away, you can plug this in. We have f of 0 equals a. And so we have 0 minus 2. And again, be careful. I'm missing another. I always look back and forth. I'm missing that exponent of 2, huh? I keep missing that. So don't forget that. That's going to cause some issues if we do. Okay, so I have 0 plus 3 times 0 minus 4 squared. Don't forget that square. And when you do plug in your f of 0, that ends up being equal to the y value. It's equal to 1. That's what f of 0 is. So we've got ourselves a mini equation. Let's kind of clean it up a little bit. We still have a involved. Now 0 minus 2 is negative 2. 0 plus 3 is 3. And we have negative 4 squared, still equaling 1. Clean it up just a little bit more. We have a negative 2a. And 3 times negative 4 squared, 3 times 16, still leaves us with a 1. So if we're going to clean this up, what do we have? Negative 2 over 48 with an a. If you'd like to reduce it, we have negative 1 over 24a equals 1. And solving for a finally, multiply by the reciprocal, we get a equals negative 24. So we're almost there. That is our stretch factor. So let's replace this, our final function. See if I can write this in. I'll keep it at the top. A should be negative 24. And I'll move this over just so that we're very clear that it's being multiplied to the entire function. Here we go. There we go. Negative 24 multiplied by the entire function. Now you can decide whether you'd like to put this into the numerator or out towards the edge. Whatever's easier, but I know alternatively you could see it in the numerator as well. So maybe it's easier for us to punch into our TI to help us see what the function is. So let's test it. We have that technology. Let's take a look at that. And I could start all over if I'd like to, but I could also use insert key. So again, if I'm going to insert a couple of things, you could either decide that it's negative 24 multiplied by the entire function, or we can insert it in the top, but we still have to enclose the entire numerator in parentheses. So let's go with, I think it's easier to enclose the entire numerator in parentheses so I don't have to move to the edge of the screen on the right. So I'm going to insert second delete. That allows me, let's say that we're going to open up another parenthesis. I'm going to insert negative 24. So that's the numerator. But remember, I have to enclose the entire numerator inside parentheses so that we're really clear with the rational functions. So one more insert, second delete. and I have a closed parenthesis. So that gives me my entire numerator inside parentheses, and I don't know if you can see this, but maybe if I were to move the screen, I can't move the screen over. You'll see that you have the entire denominator in parentheses. Maybe I can. Sometimes it's a little harder. Nope, can't do that. Hope you're playing along. You'll see for yourself. But let's finally graph this, and this is what I'm really excited about. Look at that. If we'd like to, maybe I can make a copy of this. Sometimes I can. Screen capture. I know you're seeing this. But let me see if I can put this really close to our actual graph so that we can really see, did we do this correctly? Let's paste it. Oh, sometimes it pastes off the screen. I want to move this into your viewing window. And look at that. We are pretty close. We're actually very close depending on where we're at. So look at, we have that y-intercept at 0, 1. We look, the two left branches on both of them are quite nice. And the right branches kind of look like they're following the same pattern. So this is what we'd have to do in order for us to use a graph to write an equation of the function. Just a quick summary. Use your vertical asymptotes to help you out with your factors that should be in the denominator of your rational function. Use the behavior of the function around the asymptotes to help you figure out the multiplicities in the denominator. If you want to figure out the factor in the numerator, use your x-intercept. And the multiplicity has to do with whether it crosses the x-axis or bounces off the x-axis. And for stretch factor purposes, you use a point on the graph and plug that into your function to help you figure out what that number is. We call the stretch factor A. So I hope this helps. I know there's a lot of information here, but it's just super useful. I know we're using the TI to help us, but it's super useful when you don't have a calculator in hand. I'll see you in the next example.